Okay, so this is the review session for EGME 442, Computational Cardiovascular Biomechanics, Midterm 1 for Spring 2021. Okay, so I looked up at the poll on Canvas, and these were the two, by far the two most leading requested topics, which was lump parameter modeling and arterial biomechanics. And so over the next hour or so, maybe hour 15, I'm going to be reviewing these topics to help you out for the midterm. I especially want to do, at least, a couple examples with the lump parameter modeling, just to give you an idea of what you can expect for the midterm exam. Okay. All right. And so first, let's go over lump parameter modeling. Right. And so this is, I think, probably the most recent topic that we went over in the class, the last one that we covered before the midterm. And the whole idea with lump parameter modeling is to use circuits to provide a kind of a simple, model or simple representation of blood flow. And so I say simple, but everything's always relative, right? So it's relatively simple, but even lump parameter modeling can still get extremely complex in itself. And so the reason we use circuits is that it's very elegant in its approach, right? And so there's a ton of parallels in between, first of all, just just fluid mechanics and circuits, but there's kind of another level to this where, like, especially cardiovascular fluid flows, which has a lot of certain features, a lot of features in circuits kind of match together along with that. And so, kind of the upshot for this is that, we eventually we're leveraging the analogy between circuits and fluid mechanics. Right. Okay. And so basically the idea is that, if you have a certain blood vessel, whether it be branching or something like that, we can then, replace this or represent this as a certain circuit type. Okay. And so, I think the example that I have in the lecture notes looks something like this, right? So let's say that we have a branching vessel, okay, right? And then now let's represent this with the circuit, right? So let's say that the circuit, might have some inductance here, then has, its resistance and capacitance, right? And then the path is going to split, right? And so let's say that, on this side here, we just only have resistance and capacitance, right? And so basically, for every blood vessel or every, segment of blood, you can replace it with a collection of circuit elements to emulate its behavior, right? And the reason we do this is that, this representation on the right here with the circuits, relatively speaking, this is a lot easier to solve and to analyze than kind of a full fluid mechanics situation, right? And the primary reason for this was that circuits, if you're just considering linear circuit elements, in order to govern this behavior, we only need a set of ordinary differential equations. Okay, fix this word right here. Okay, so circuits are governed by ordinary differential equation, which, are still not a walk in the park. So, you know, ordinary differential equations are still differential equations. But the nice thing about this is that, you know, ODEs, you know, compared to PDEs are a lot easier to solve. And in fact, you know, there's a lot of packages within, you know, say like MATLAB or Python that allows us to solve these guys, you know, very, very easily. Okay. Okay. And so in particular in this class, you know, we've used, you know, we primarily use MATLAB. And so, you know, we can use ODE 45 for that. You know, but there's lots of other packages out there that exist. Okay. All right. But, you know, for the purpose of this exam, you know, you're not going to be solving any of the differential equations. All I want you to do is just set up the equations, you know, take a circuit, you know, and tell me which, how do we actually represent this with, you know, with governing, with its ordinary differential equations. Okay. Okay. All right. And so now let's talk about the circuit elements and, you know, what they physically represent. And so we're going to be primarily working with 3 circuit elements. And so these, you know, are the 3 linear circuit elements, just because, you know, they're kind of the simplest ones to deal with. And each of them, you know, besides their mathematical effect on their equations, each of them have something physical that they represent about blood flow. Right? And so, you know, this part's really important because you know, not only do I want you to remember, you know, how to work with these mathematically, of course, in order to derive the equations, but you should also understand, you know, what they physically represent, because, you know, that's kind of the reason why we use them. All right, and so the first element that we went over was the humble resistor. Okay. Right. And so the idea with the resistor is that this represents the fact that, you know, blood is a viscous fluid, and whenever you have blood that flows into a pipe, there's going to be some viscous friction losses. Okay. When I talk about losses, what I essentially mean is energy losses. Okay. Okay. And so schematically, we represent it like this, right? And so it's just a line with like some sharp squigglies. Okay. And then the equation that we use for this, or to govern this, its behavior, is its Ohm's law, basically, right? Right. And so the Ohm's law basically looks like this. So we have P1 minus P2 is equal to Q times the resistance, right? And what that basically represents is that if you have a pipe like this, right, in order to drive a certain amount of flow, because that's what Q represents flow. In order to drive a certain amount of flow through your pipe, you know, the pressure needs to drop from P1 to P2. Okay. And that drop in pressure, so pressure, you can almost think of it as like, you know, drawing kind of the analogy to physics, pressure is almost like the same thing as like potential energy, right? So pressure is basically, you know, energy that the fluid can tap into that they can convert into kinetic energy if it needs to, okay? And so, you know, in order to get through a certain pipe segment where there's, you know, viscosity and viscous losses, you know, the fluid kind of has to, you can almost think of it as like, it has to spend some pressure energy. So it has to, you know, take some pressure money from its wallet, spend a little bit of it, and then, you know, then the pressure drops from P1 to P2. Okay. And so, you know, these viscous losses are always present, you know, whenever you have flow of any fluid within a pipe. But you know, where they're most pronounced and where, you know, you see the highest amount of viscous losses is in the tiniest pipe, right? And so in other words, you know, the capillaries. So your capillaries are extremely small. And so that's generally where you have the most resistance in your system. Okay. Okay. And so that's the resistor. And so the resistor, remember, is unique because it's the only one that is not governed by a differential equation. Okay. Next, we have the capacitors. Okay. And so capacitors, they represent the fact that, you know, our blood vessels are flexible and that they can temporarily store flow. Okay. Because if you think about what a capacitor does in, you know, in a circuit, so a capacitor, you know, looks something like this. So, you know, usually it's, you know, two parallel plates, and there might be some dielectric fluid in the middle of it, right? And what can happen is that as, you know, as current flows into this, you know, some of that charge can be stored within those parallel plates, right? So it's almost like a you know, not really the same, but, you know, same idea is kind of like a battery, right? So a battery can charge, you know, can charge electricity or store it and then kind of discharge it later, right? And so same thing, you know, when we have you know, flow coming into a blood vessel like this, okay, what can happen is that, you know, the fact that, you know, our blood vessel is flexible, it almost acts like a tiny balloon, right? And so you can see that it inflates kind of like that, right? So the blood vessel is going to inflate, and then it's going to, you know, collapse on itself again after. Okay. All right, and then and so the equation that we use for this is basically is a relationship between the time rate of change of pressure on a capacitor and the flow rate going into the capacitor. And so the governing equation is dP dt, where P here is the pressure on the capacitor. So we're forming a relationship between, you know, the time rate of change and the flow. Okay. Right. And then we have this factor out in front called 1/C, where C here is the capacitance value of the capacitor. Okay. All right. And so when we deal with capacitors in our one-parameter circuits, you know, usually we're going to deal with this equation where we, you know, we're going to introduce a time derivative term dP dt, and then this is going to equal to, you know, the flow going into the capacitor. Okay. All right. And so that's the capacitance, right? And then the last element that we went over was inductors. Okay. And so inductors, you know, what in circuits, what they do is that they, you know, because of the electric field that gets inducted, you know, within the inductor, like it's basically just a wire coil, they can represent, what they can do is they can help slow down or impede changes in current. Okay. And so it's the same thing for blood flow. And so what inductors represent is they represent the fact that blood has a certain amount of mass. And, you know, whenever you have a certain mass or something, that's going to have inertia. Or in other words, you know, if you think about what inertia represents for solid objects, inertia represents, you know, the fact that you know, objects don't like to change their motion, right? So if an object is still, it takes, you know, a little bit of time and a little bit of effort to really get it moving, right? So you don't, you know, when you push on something, it doesn't just go from 0 velocity to max velocity right away. Usually there's some kind of ramp up time. So you're kind of pushing it, and then eventually it starts to gain momentum, and then it goes up from there. And so, inductors represent the same thing for fluids. Okay? And so schematically, they're represented by a little coil like that. Right? And then the equation that governs it. Right? And so instead of being a time derivative on the pressure, what we have is a time derivative on the flow instead. Okay. And so what we have is dq dt, and that's equal to 1 over L P1 minus P2. Okay. Where P1 and P2, that's the pressure drop that's on the inductor. Okay. Right. And so, if you can contrast this with the resistor, right? So with the resistor, if you have a pressure drop on it, so P1 minus P2, that's instantly going to drive flow through the resistor. But what the inductor basically says is that, if you have a pressure difference on here, what you're not going to affect here is not the flow, but the time rate of change of the flow. So that causes it to go up a little bit from there. Okay. Okay, and so that's the all the different circuit elements. Now let's see how they all work together in deriving LPM equations. Okay, and so what I'm going to do next, I'm going to do a couple examples here that kind of show you what you can expect, what kinds of problems you can expect to have on the exam. Okay? All right. And so the way these problems are going to go is essentially I'm going to give you a circuit layout. And then what I'm going to ask you to do is to essentially derive the set of ODEs that govern. Okay. All right. And so let's start with let's see. Let me start with an example that we did in class, but let me modify a little bit, and I'll give you kind of a slightly different look. Okay. And so let's start with the situation that looks like this. Right? So let's say that we have vessel coming in, and let's say that we have an inductor. Okay. And so this is going to be example 2 on the lecture notes, but I'm going to add a little bit of a wrinkle to it. Okay. And so I'm going to add a resistor right here. Okay. Okay, and then from here, the flow is going to split. And so we're going to have here a resistor. Here we're going to have a capacitor. Okay. And then we're going to go to ground. Okay. And so let's label all of these guys. So let's say that this is L. We'll call this R1. Call this R2. Call this C. Right. And then at the inlet right here, let's say that we have an inlet pressure. We'll call it PIT. Okay. And then one more thing that I'll note here is that because this node right here is connected to this capacitor through a wire, this the pressure at this node right there is going to be PC. Okay. And of course, we're going to label the flow through this inductor QL. Okay. All right. And so for these kinds of problems, you don't actually need the expression for PI because we're just deriving the equation. And so I'm not giving you numbers for any of these. I'm just interested in seeing, whether you can take this and derive the equations that go with it. Okay. Okay. And so you can see, first thing that we have to do here is we have to basically count the number of equations that we need to solve for. Right? And remember, the way that we do that is we count the number of inductors and capacitors that we have in our circuit. Okay. And then this number right here will tell you how many equations that we need to solve for in the end. Okay. And so here, we can see that we have one inductor and one capacitor. And so this tells us that we're going to need to find 2 equations. Okay. And so let's start with the upstream node. So let's start with the inductor. Okay. Okay. So normally when we have inductors here, what we do is we take the pressure difference between, at the front end of the inductor and the back end. Okay. But here, we have a little bit of a wrinkle because, if we want to take a pressure, the pressure difference, the upstream pressure we know because the upstream pressure is PI, which is the inlet, but we actually don't know the pressure here downstream. Okay. We know the pressure after the resistor. So we know after the resistor, the pressure is going to be PC, right? But, because we have that resistor there, this intermediate pressure in between the inductor and the resistor is not going to be the same as PC, right? And so we're going to need to, adjust for this a little bit, okay? And so in these situations, where you have an inductor and you don't know what the pressure is, right after it, what you can do is you can take a pressure difference, between two points that that also includes the inductor. Okay. And so in this case, the 2 points that we're going to consider is obviously, one is going to be PI, which is going to be the inlet pressure. Okay. And the next point that we know is actually going to be PC. Okay. Right. And so, if we take the pressure difference between PI and PC, the inductor is included on this path, right? But we're also going to pick up that resistor as well. Okay. All right. And so the way that we're going to deal with this is that, by taking the pressure difference between these 2 points, what we're going to do is we're going to basically, adjust or pick up all the circuit elements that we go over. Okay. Okay. And so, first thing that we're going to cross here is the inductor, right? And so the inductor is going to be, the equation for that is going to be L dQL dt. Okay. Right. And the other thing that we pick up is the pressure drop on the resistor. Okay. And so the pressure drop on the resistor, we're just going to use Ohm's law for that. And so Ohm's law is just going to be QL times R. Okay. All right. Okay. And so if we do both of those things, now we can have an equation here to solve for that. Okay. Okay. And so let's go ahead and take this expression and then solve for the time derivative here. Okay. And so if we kind of manipulate this expression, and so we're going to move QLR over to the other side of the equation, what we get is the following. Right? And so we have L dQL dt is equal to PI minus PC minus QL R. Oh, I should label that resistance. It should be R1. Okay. Right. And so now we can divide both sides by L, and this will give us our first differential equation for the flow on the inductor. Okay. So we have dQL dt is equal to 1 over L PI minus PC minus QLR1. Okay. And this here is our first equation. Okay. And so it's a little bit modified compared to, our regular, inductor equation. And that modification comes from the fact that we also have to cross over this resistor, in order to get there. Okay. All right. And so you notice, for the pressure drop on the resistor, I use QL for this expression, right? And the reason I use QL is that, because these guys are connected in series, whatever flow that goes over this resistor is going to be the same flow that's on the inductor, right? So there's only one single path here. And so the fact that there's only one single path means that, you know, the flow that goes over this resistor has to be the same flow that went over the inductor as well. Okay, and so that's the, you know, that's the first equation. And so now the second equation for the capacitor, the way we're going to get that is by applying conservation of mass to that point where it junctions off. Okay. Okay. And so conservation of mass looks like the following, right? And so if we kind of draw that junction here, right? And so coming into this junction, we have QL, which is the flow on the inductor. Up top here, we have R2, sorry. Okay. And on the bottom here, we have QC, right? And so by conservation of mass, what we're saying is that, you know, the flow, you know, all the flow in has to equal all the flow out, right? So the flow coming in is going to be QL, and this is equal to QR2 plus QC, okay? And so in order to complete this expression, what we're going to do is we're going to replace, you know, our QR2 and QC with their appropriate, you know, lump parameter model equations, right? All right, so let's start with QR2. And so QR2, you know, the way we're going to find that flow is we're going to take the pressure difference across this resistor. And so the pressure difference, you know, upstream here we have PC, and then downstream here we have ground. Right? And so the pressure difference across this resistor is going to be PC minus 0 for ground divided by the resistance value. And so we have PC divided by R2. Okay. All right. Next, we have QC, and so for QC, we're going to just input the equation for the capacitor, and so QC is going to be C dP C dt. Okay. And so now all we have to do is just plug these into this expression up here, and then manipulate it a little bit mathematically, and then that will give us our second differential equation, you know, for the circuit. Okay. And so putting it all together, what we have is QL is equal to PC over R2 plus C dPC dt, right? And so just like we usually do, we're going to solve for the time derivative here. And so we're going to solve for dPC dt, right? And so dPC dt is going to be equal to 1 over C times PC divided by R2, or sorry, is going to be QL minus PC over R2, right? And then we put a box around it, and then that's our second equation. Okay. All right, and so that's, you know, just a slightly modified version of, you know, the example that we did in the class, but, you know, it's just, you know, hopefully just giving you another look of, you know, how we actually derive these equations. Okay. All right, and so now let's now let's do an example that we didn't do in the class. That's going to be a little bit more complicated. All right, and so for here, you know, let's say that we have the following situation, and so let's say that we have, you know, flow coming in here, okay. And this flow is going to hit a capacitor, okay. And then it's also going to go to another path, and so we'll call this R1, we'll call this C, okay? And then from here, the path is going to split, and on one path, we're going to have an inductor, and another path, we're going to have another resistor. We'll call this R2, okay? This goes to ground, and in fact, this also goes to ground right here, okay? Let me clean this up a little bit. And so that first capacitor there, you know, the second end of it goes to ground. Okay. All right. And so, you know, this is actually be a little bit more of a you know, complicated situation. Right, so let me label some things here. So first thing I'm going to label here is the pressure on the first capacitor. Okay, so we'll call this PC. Okay. Another thing that we're going to need here is we're going to need the pressure at this node right here. Okay? And so this is not something that, you're not going to get a differential equation for this node, but, what you'll see is that this node will be, this pressure will be kind of key in a lot of our calculations, okay? And so, don't be afraid to do this in your problems too. So if in your problems, if you find that, you're having trouble writing out the equations, write down kind of a temporary or auxiliary variable to kind of help you out. Okay? Eventually, because this is just a temporary variable, eventually we want to eliminate this from our equations. But for now, we'll just kind of keep it there because it kind of makes things convenient at first. Okay. And the reason I'm putting this there is just so that we can compute a pressure drop on this resistor, a pressure drop on this resistor, and a pressure drop on that inductor. Okay. Just having a temporary variable right there just kind of makes things pretty, go a little bit smoother. But we're eventually going to have to solve for it. We're going to have to eliminate it. Okay. Okay. All right. And so, let's go about solving this this circuit, right? So first thing we always do is we count the number of inductors and capacitors. And so in this case, we have two, and so just like the last problem, we're going to have two equations here. Okay. And so let's go ahead and go ahead and start solving for this. Okay. And so the first thing we want to do is we want to solve for the let's do a differential equation for the first capacitor. Okay, so let's do conservation of mass at this node right here. Okay. Usually, a good rule of thumb is that whenever you have a path that splits in your LPM, usually it's a good idea to form a conservation of mass there, and then that's usually going to help you out with some equations. Okay. Eventually, we're going to do conservation of mass here as well at the second junction, but let's start with this one here first. All right. And so just like before, we're going to have all the flows in is going to equal to all the flows out. Right? So coming in, we have Qi of t. Okay. And then coming out, what we have is the flow over the capacitor, so we'll call that Qc, plus the flow over the resistor, so we'll call that Qr1. Okay. All right, and so just like we usually do, we're going to replace Qc and Qr1 with their expressions. Okay. So we have Qi of t. Qc here is going to be dpc dt. Okay. And then Qr1, this is the flow on the first resistor. This is going to be Pc minus Po. Okay. Notice here I'm using that temporary pressure divided by R1. Okay. And then now what we can do is we can solve this expression for dpc dt. Okay. And so if we do that, dpc dt is equal to 1 over c times Qi of t minus Pc minus Po divided by R1. Okay. Okay. And so that seems okay, right? But right now, what we have here is this Po, and so we can't leave it in that form. And so we need to solve for an expression for Po. Okay. And so to do that, what we're going to do is we're going to apply conservation of mass at this downstream node right here. Okay. All right. So we're going to be solving for PO using downstream junction. Okay. All right. And so at this downstream junction, let me draw it out right here. Okay. And so coming in here, we have QR1, so the flow coming from resistor 1. Up top here, we have QL, which is the flow on the inductor. Okay. And then the bottom here, we have QR2, which is the flow on the second resistor. Okay. Right. And so what we have, we're going to perform conservation of mass. And so coming in here, we have QR1, then we have QL, then we have QR2. Okay. QL is already fine. And so, QL is already going to be the flow on the inductor, which we're going to solve for. But let's go ahead and replace, expressions for QR1 and QR2. Okay, so QR1, it's going to be the same as before. It's going to be PC minus PO, all divided by R1. Okay, then we have QL, and then QR2 here is going to be PO divided by R2. Okay, all right. And so now let's take this expression and let's solve this for PO. Because the nice thing about this expression here, everything else besides PO is a known quantity or something that, something that we want to leave in the final equations, right? And so, we have R1 and R2, and so those things are known, and so, we can leave those in there. And we also have PC, which is the pressure on the capacitor, and so that's, obviously something we're going to solve for. And we also have QL, which is something that we're going to solve for as well. Okay. Okay. And so if we solve for PO, let me go ahead and put PO all on one side of the equation. What we have is PC divided by R1 minus QL is equal to PO. And then we go ahead and factor out 1 over R1 plus 1 over R2. Okay. And so what we get here is PO is equal to PC over R1 minus QL divided by 1 over R1 plus 1 over R2. Okay. All right. And so what you can do now is that now you have this expression for PO, we can go ahead and plug this back in to the equation that we had on the previous page. Okay. And so basically we're going to plug PO in for this guy right here. And so, obviously it's going to be a little bit of a mess. And so it's going to be a lot to plug in. But you can do it. Right? And so for the exam, if I give you a problem like this, you can leave things in terms of this. And so, you can say that, here's PO, and then I'm just going to plug this back into here. And so you don't have to actually go through the trouble of actually plugging it in. And actually, if you're solving this with MATLAB, you can just kind of make a new variable for PO anyway. And so that's going to be fine. Okay. But the important thing is, I at least want you to solve for an expression for all of your auxiliary variables here. Okay. And so that's the, that's the expression for the capacitor. Now let's find an expression for the inductor. All right, and so for the inductor, here we just have kind of a very simple situation. We're just going to do the pressure drop on the inductor and set that equal to, 1 over L times dQL dt. So we have dQL dt is equal to 1 over L times the pressure drop on the inductor. And so if we go back to our original diagram, you can see that the pressure drop on the inductor, so upstream here we have PO, which is the one that we solved for, and then downstream here we have ground, which is going to be P is equal to 0, okay? And so actually our inductor equation is going to be 1 over L times PO. where, you have PO solved on this page right here. Okay. And so again, you don't have to go through the trouble of plugging in for PO right here. As long as you would solve for it, in another part of the problem, then I know, basically where to look for it. Okay, and so hopefully that example was helpful, just to kind of give you another look at a certain kind of equation and what to do when you need to solve for a certain auxiliary variable like this. Okay, and so that took up quite a bit of time, and so that almost took up 45 minutes. And so maybe for the next 20-30 minutes or so, let's review arterial biomechanics. All right. And so the lecture notes on arterial biomechanics was, there was a lot. And so there's kind of a lot going on that lecture notes, okay? But kind of the main categories that I want you to pick up from this are, the first category is, first of all, just, what the pressure and flow waveforms look like in the cardiovascular system. Next, there was a section on the Windkessel model, and so I want you to go over that. Not necessarily the experiment itself, but more, what does the experiment kind of physically represent? Okay. The third kind of big topic here was the whole thing with wave propagation. And then the fourth big area that we went over here was that I want you to know for the exam is Mechanotransduction. There's also everything at the end with allometry, but we're I can tell you right now that allometric relationships are not going to be on the exam. Okay, and so let's go over each of these sections individually, and then kind of talk about what kind of the main points are. Okay, so let's start with the pressure and flow waveforms. And so the main thing that I want you to get from the pressure and flow waveforms is the fact that they're pulsatile. Okay. And so what that basically means is that, that they're going to go up and they're going to go down. And so they're basically going to oscillate. And this correlates with the fact that your heart, has to pump and then has to relax and then has to pump and then it has to relax. Okay. Okay. And so, the waveforms kind of look like this. So for the pressure, we had the pressure kind of rapidly goes up, and then we have a little bit of a notch, and then it kind of slowly decreases. Okay, so this is pressure. Okay. And then the flow waveforms, are a little bit more extreme. And the flow waveforms kind of look something like this, right? And so you have a large amount of flow, when the heart is contracting during systole, and then basically no flow during diastole when the heart is relaxing. Okay. And that's two other terms that I want you to know for this exam too. So systole and diastole, right? So remember, systole is what happens when the heart is pumping, and then diastole is what happens when the heart is relaxing. Okay? Systole is pumping, diastole is relaxing. Sometimes I get the words kind of jumbled up in my head. Okay. And so this section right here, when the pressure is going up, this here would be systole. Okay. Whereas this next section right here, when the pressure is going down, this here is diastole. Okay. And so kind of know what those terms are and what they kind of represent. Okay. Okay, so that's that's everything I want to say about the pressure and flow waveforms. Now let's talk about the Windkessel model, or at the very least, what are kind of the big upshots for this. Okay? And so a little bit of history, the reason the Windkessel model came to be a thing is because doctors were observing that these are what the flow waveforms and pressure waveforms look like in the cardiovascular system. And back then, over 100 years ago, scientists and experimentalists were having a really hard time, trying to replicate these exact waveforms because they're tough, right? And so they not only do they go up and down, but for the flow you have a system where the flow basically goes to zero during diastole, whereas for the pressure, you know there's always going to be kind of a minimum pressure that's going to be in the system. So the system is like almost always going to be pressurized, but the flow kind of goes up and down. And so scientists were really struggling to come up with an experimental setup to emulate this. Right? And so that's how the Windkessel model was born. Okay. And so visually it looks something like this. And so first thing that was there was some kind of pump. And this pump was kind of cyclic in nature to kind of represent the heart. I think even in the early days, what they had was just a hand pump, just a dude just pumping it with his hand every now and then, right? Okay. Next thing that they had was kind of like a water balloon, and so they call it was just an elastic chamber. And at the end of the Windkessel model, what they had was a bunch of channels, a bunch of very thin channels, right? And what this was it provided flow resistance. Okay. Right. Right. And so the way this works is that when the pump pumps, or when it ejects flow, a lot of that flow is going to go into the elastic chambers, right? And so the elastic chamber is going to inflate, and some flow will still go downstream, but not that much. And then over time, the pressure or the elastic chamber is going to kind of deflate, and that's going to lower the pressure. Okay. And so kind of the upside, the upshot to this was that this was kind of the first time that scientists have kind of separated these two kinds of behaviors, right? And so the first behavior that we had here was this elastic chamber. And what this elastic chamber represented was the fact that your blood vessels and your arteries are flexible, and what they can do is they can temporarily store flow. So we're kind of talking in this review, we're kind of talking about it backwards because we've already talked about the capacitance and parameter modeling. This elastic chamber is basically the same thing as that capacitor. Okay. And through this experiment, scientists were basically able to see that, being able to capture this compliance, or being able to capture this kind of flow storage, feature is essential, and one of the core features of cardiovascular blood flow, right? And so basically all future models of cardiovascular fluid flow, had to include some kind of compliance element or some kind of flexible element. And the Windkessel model was kind of the first ones to do this. All right, and so the second element that's essential here is all this downstream resistance. Okay. Okay. And what these do is that they basically require that there's always basically a mean flow a non-zero mean flow in your blood. Okay? Or non-zero, I'm sorry, non-zero mean pressure. And physically, what these represent is these represent the viscous resistances of all the downstream capillaries. Okay. And so, just like in the experiment, the downstream capillaries are extremely small, and they're going to contribute a lot of this viscous resistance. Okay. All right. And so, from this Windkessel experiment, what scientists have found that these two features here are kind of the core features of cardiovascular fluid flow, that a lot of that models need to be able to capture. Okay. All right. And we see these features exactly in our lump parameter modeling, right? So in our lump parameter modeling, it's actually the correlation is so one-to-one, it's almost insulting in a way. So for the compliance, we obviously have our capacitor that represents this, and then for the resistance, we have our resistor, which represents exactly that. Okay, and so this lump parameter modeling, a lot of its inspiration came from this Windkessel model. Okay, so that's the Windkessel model. And so now let's talk, very briefly about wave propagation. And so the idea with wave propagation was the fact that, because our blood vessels are, flexible, and because of the action of the heart, where the heart is kind of, pump and relax, pump and relax. Okay. What tends to happen is that, you have these pressure pulses that travel along the walls of your blood vessels from the heart down to the capillaries. Okay. And then what's going to happen then is that these pressure pulses are going to reflect off of the capillary bed, and then they're going to travel back up the tree. Okay, and so the analogy that we use for this is a pulse traveling along a string. Okay? And so say that you have a string that's attached to a wall, or maybe it's attached to your guitar, right? So that's kind of the big example for this. Okay. And because this string is flexible, what happens is when we put a pulse on the string, we have a wave that shows up, and this wave is going to travel down the string at a finite speed. And then eventually what's going to happen is that this pulse is going to reach the wall. It's going to hit the wall and it's going to reflect and it's going to come back up the string. Okay. Okay. And so that's the reflected pulse. Okay. All right. And then as this reflected pulse comes back, it's going to interact with the next incoming wave. So let's say that we're constantly kind of doing this with the string, and so we're constantly sending pulses, and so we have this kind of interaction between the forward-going waves and the backward-going waves. Okay. And so the same thing happens in our cardiovascular system. So in our cardiovascular system, we have these forward-going waves that originate from the heart and travel along your blood vessels until they reach your capillaries. They're going to reflect off the capillaries and then start coming back up. Okay. And this is always kind of constantly happening. And so, what you have is, this interaction between, the forward-going waves and the backward reflecting ones. Okay. And so in reality, it's a fairly complex process just because, you have waves that are always going down there. You have waves that are constantly going back, but the vessels, bifurcate quite a bit. So the bifurcations add, quite a bit of complexity to it. And so, we didn't get into, the really big specifics of, how these waves reflect or not. Okay. But, we did talk about kind of the overall effects that you can kind of expect from wave propagation. Right. And the overall effects that you observe depends on how far you are from the heart. Okay. All right. And so the first one that we stated is that as you get further away from the heart, what tends to happen is that the peak systolic pressure tends to increase. Okay. And so if you measure the peak pressure, somewhere right next to your heart compared to, somewhere maybe in your arms or your legs, you're going to have a higher, peak systolic pressure. Okay. All right. So number two, and so the other overall effect, which is due to reflected waves, is that as you get further away from the heart, right, so as you get further away from the heart, the peak systolic pressure will be delayed relative to areas closer to the heart. And again, this is a consequence of the wave interactions. And so if we kind of draw kind of two comparison graphs, okay, and so let's say that this here is near the heart, and so this here is far from the heart. Near the heart, you might have a pressure waveform that looks like this, but then far away from the heart, you might have a pressure waveform that looks like that. Okay? And so obviously, this is exaggerated, so it's usually not this pronounced. But you can see here, far away from the heart, you have a higher pressure up here, and that higher pressure occurs, a little bit later on in your heart cycle compared to before. Okay. And so that's the wave propagation part. And so now let's finally talk about Mechanotransduction, and then I think we'll close the review session from here. Okay. All right. And so the idea with Mechanotransduction is that your blood vessels are lined with living cells, right? And these living cells will, they can sense, or they can, they can feel all the forces that the blood imparts onto them. Okay. Okay. And so as the blood, flows in your blood vessels, they're going to exert, several different kinds of forces. And so the first force, because the fact that blood is a pressurized flow, there's going to be pressure forces that kind of push on the outsides of the blood vessel. So we call those normal forces, right? And so in addition to that, there's also going to be the viscous, shear stresses that the blood also imparts on the wall. So as the blood flows past, there's going to be some friction, on the vessel wall. Okay. Right. So all the blood, your blood vessel, your vessel, wall cells can feel all these forces. And it's basically feeling these forces, all the time. And so there's basically no time when they don't feel them, right? And so, remember in the class what we say is that your blood vessel, or your blood vessel cells, they're very similar to engineering students, so they're kind of always under a state of stress. All right. But the thing about your blood vessel wall cells is that they like to be kind of comfortable in their in their state of stress. Okay. And so what that means is that whatever stress, whatever they define to be normal, a normal amount of stress, right, kind of a normative amount of stress, they like to maintain that. Okay. Um, And so, whenever something happens in a cardiovascular system that adjusts, that changes this, like maybe the amount of blood flow changes, or maybe you start to have high blood pressure, what will happen is that your blood vessels will actually adapt its shape and change its shape in order to kind of restore the same amount of stress that it had before. Okay. And so, what we did in the class was we looked at three kind of examples for, how the blood vessels actually adapt its geometry or changes its geometry, depending on, when a certain force is outside of its normal range. Okay. All right. And so first, let's talk about the wall shear stress. Okay. And so wall shear stress, remember, that's the term that we use for the viscous amount of wall shear of viscous force that the blood imparts on the vessel wall. Okay. And so your blood vessels like to keep basically the same amount of shear stress. And actually, if you remember when we talked about Murray's law, what we saw was that, throughout your entire cardiovascular system, all the blood vessels in your body, they all like to have the same level of wall shear stress. Okay. And so if something happens where the wall shear stress is kind of either too high or too low, and this occurs over a long period of time, then your blood vessel will kind of react to this. Okay. Right. And so let's say that we have a normal blood vessel here on the left, and let's say something happens where the wall shear stress is too high. Maybe your blood is kind of outputting a lot more blood than usual, and so the flow rate is more. Okay. Or maybe there's some kind of disease that's happening in your blood vessels, where it's causing a higher amount of wall shear stress. Okay. And so in response to this, if your blood vessels sense that the wall shear stress is too high, in order to kind of spread this wall shear stress out over a larger area, and also to kind of reduce the amount of flow velocities, what your vessel will do is that your blood vessel will expand. Okay. Right. And then the opposite will happen if the wall shear stress is too low. So if the wall shear stress is too low, what the vessel is going to do is it's going to constrict. And what it hopes to do there is it hopes to kind of concentrate the velocity path lines in order to make sure that in order to basically increase the amount of wall shear stress. Okay. I should be more clear here. So when I say vessel expands, what I mean is the vessel diameter expands. Okay. Okay. And so that's the wall shear stress. And so that's how the blood vessel responds to that. Okay. And so the next thing that we covered was the vessel length. Okay. Okay. And so basically a blood vessel will lengthen whenever it feels too much tensile stresses. And so, every human being, experiences this, at some point in their life, because, every human being goes from, a tiny baby into, a relatively larger adult, right? And so as your limbs grow and as your bones grow, what that's going to happen is that it's going to stretch out your blood vessels, right? And so, in response to this, your blood vessels will basically feel that tensile force. They'll be like, ooh, that's too much force. That's too much for me to handle. Then what it'll do is it'll, basically add more cells to the vessel wall so that it kind of expands from there. Okay. And so with a longer vessel, that basically conforms to your longer limbs, then that tensile stress is kind of relieved. Okay. Okay. And so the last one that we talked about was the response to pressure. And so pressure, remember, it puts out a normal force on the vessel wall. Okay. Right. And so schematically, it looks something like this. Okay. And so the result of this normal force is that this is going to induce circumferential stresses around the vessel wall. Okay. And so, the way that your blood vessel will kind of alleviate these circumferential stresses, if it finds something that's, too, outside of its normal ranges, what it'll do is it'll change the thickness of the vessel walls. Okay? Right. So let's say that we have, a normal blood vessel that looks like this, right? And so I drew kind of a donut here to just to kind of illustrate the fact that your blood vessels have thickness to them. Okay. Right. And if the pressure forces are too high, so let's say that you have high blood pressure, you have hypertension. Okay. Right. And so if the pressure increases, what that's going to do is that it's going to induce much higher circumferential stresses around your blood vessel wall, right? And so to alleviate those stresses, what it does is that it makes the vessel wall thicker. And so, for patients with high blood pressure, this is kind of a bad thing because if your blood vessels, if this kind of continues on, your blood vessels get too thick, then that can kind of lead to a lot of negative consequences. Most notably, your blood vessels tend to get even more stiff, and then they're kind of hard to adjust to certain things, and that leads to a lot of long-term health consequences. Okay. And so the opposite is also true at first too. So if you have too low pressure, then what's going to happen is that your vessel wall is going to thin. All right. Okay. And this whole idea that your blood vessels will respond to forces, this is called Mechanotransduction. Okay. Right. Okay. And so that's all that I have for the review. So it ran a little bit long, but hopefully this was helpful to everyone. And so best of luck for studying for everyone. If you have any more questions, definitely reach out to me. And I'll see you guys later today.